Okay, in this video, we're going to talk about complex numbers some more, and we're going to continue to talk about converting from standard form to trig form, but instead of decimal approximations, we're going to be using exact values. So we are going to be taking a plus bi, which is a complex number in standard form, and converting it to r times a quantity cosine theta plus I sine theta. Now, before we had r and theta with decimal approximations. This time we are not going to do that. Now, we are going to have the same conversion factors more or less. R is going to be equal to a squared plus b squared. And before we had that tan theta should be equal to b over a. We're not going to do inverse tan this time. We could, but because we're doing this in radians, you're using inverse tan in the calculator gives a decimal approximation. It's a little harder to do. So what we're going to do instead is leverage our knowledge of tan theta to get two values, and then one of them will be the right one. So we still have the same restrictions that theta is in between 0 and 2 pi, and r is going to be something positive. And we're going to take advantage of the same thing that we were doing before, which was graphing our point in standard form to know what quadrant it is, and then we'll know which angle actually is the right one. So let's just dive right in and do some examples. So let's consider 3 plus 3i. So the first thing I'm going to do is find the r and the theta. So r is equal to the square root of 3 squared plus 3 squared, which just simplifies down to square root 18. And remember, we're not going to get a decimal approximation. If we were required to, we could reduce this radical a little bit, but I don't think we're going to be required to. And then we're going to find here tan theta. Now this is tan theta, so it's b over a, right? So it's 3 over 3, which is 1. All right, well, where is tan theta 1? Tan theta is equal to 1 when theta is equal to pi over 4 or 5 pi over 4. Which of these is correct? This is where plotting our number comes into play. So if we plot 3 plus 3i with the real axis here and the imaginary axis here, it looks like this. So we're in quadrant 1. Which of these angles is in quadrant 1? This one. So this number, or this angle, is incorrect. So what we'll do is we will use our pi over 4 as our theta, and we have our r square root 18. So now we can write our complex number with our r and theta. So our r is square root 18, and we're going to multiply this by the quantity cosine pi over 4 plus I sine pi over 4. Okay, let's do another one. How about something seemingly easy, but it turns out to be a little bit weird? What about the number I? Okay, well, first of all, this is a little bit weird. What are a and b even here? So let's just think about how we might write this as a plus bi. Well, there's no real part and one imaginary part. So now we have our a and our b. So what are we going to do? We're going to find our r like normal. A squared plus b squared. And this is just square root of 1, which is just 1. So r is 1. Not particularly interesting, but that's fine. Well, if we find our tan theta, we get that tan theta is equal to 1 over 0. Well, this is undefined. That's kind of a problem, but not really a problem. Tan of theta is undefined in the regular domain of the unit circle at two places. Where? At pi over 2 and 3 pi over 2. So let's just diagram our point and see which of these is correct. Real, imaginary. The point is up here, And this angle is definitely pi over 2. 3 pi over 2 would have put it all the way down here. So our correct angle is pi over 2, and we can use our r and our theta. So we can write this as r times the cosine of pi over 2 plus I sine pi over 2. That one was a little tricky because of this formatting issue here. But after we see the trick to formatting, it made it very direct. Same strategy as this problem. All right. Let's do another one. What if the number is just -3? Man, that looks odd. But we just do the same thing we did last time. How would we write this as a plus bi? Well, a is the real part, which is what we have here. Now, there is no imaginary part, but the trick to that is that you just give the imaginary part a 0. So now a is -3 and b is 0. Then you just use the same tricks as before, or the same techniques rather. R is equal to a squared plus b squared, which is just 3, right? We simplify this, we get 9, square root of 9 is 3. Now, tan of theta is equal to b over a, which is 0 over -3, which is 0. Well, this means that theta could be 0 or pi. So we need to plot this point to see which of these it is. Real axis, imaginary axis, -3 in the real direction with no movement in the complex or imaginary direction. Here we are. There. Well, what is this angle? That is definitely pi. So our angle is pi and our radius is 3. So we can write this as r, which is 3, times cosine of theta, which is pi, plus I sine theta, which is pi. All right. Let's move on to one in quadrant 2. So this one is -2 plus 2i. Well, we find r like normal. Square root of -2 squared plus 2 squared. This is going to be the square root of 4 plus 4, or square root 8. And we'll just leave that. We could simplify it a little bit, but I don't think we're required to do that. Then we have tan of theta. Tan of theta is b over a, or 2 over -2, which is -1. Well, where does that happen? That happens at theta is equal to 3 pi over 4, or 7 pi over 4. Okay, so we need to graph these things and see what it looks like. So -2 plus 2i is over here. You go -2 this way, and then 2 this way, and this is quadrant 2. Which of these angles is in quadrant 2? This one. So this is the appropriate angle, 3 pi over 4. So we can write this in trigonometric form. Square root 8 cosine 3 pi over 4 plus I sine 3 pi over 4. And we converted from standard form to trigonometric form. All right, last two. Let's do one in quadrant 4. So let's do 5 minus 5i. 5 minus 5i. Let's find r first. R is the square root of 5 squared plus -5 squared, which when you simplify it is just square root 50, which we will leave. It could be simplified a little or reduced, but we're not going to worry about that. And then tan theta is equal to -5 over 5, which is -1. Well, where is tan -1? This means that theta is equal to 3 pi over 4 or 7 pi over 4. But let's diagram this guy. So, like this. Here he is. This point right here. 5 minus 5i. We are definitely in quadrant 4. So quadrant 4 is this angle, not this angle. This was in quadrant 2. So this is the appropriate angle, 7 pi over 4. And we can write our number from standard form to trigonometric form by using r, which is root 50, times the quantity, cosine 7 pi over 4 plus I times the sine of 7 pi over 4. Okay, one more. Let's look at z equals -2 square root 3 minus 2i. This one is a little bit quirky, but that's okay. This square root may be intimidating, but we just work it the same way that we always do. R is equal to the square root of -2 square root 3 squared plus -2 squared. So this turns out to be 12 plus 4, because this will be -2 squared, 3 squared, which is 4 and 3, giving us the 12. This one's just 4. So this is square root 16, which is just 4. That's pretty nice. And then we're going to find tan theta, which is b over a. So -2 over -2 root 3. These -2's can reduce, and we have 1 over root 3, or if you'd prefer, root 3 over 3 after rationalizing. And where is tan equal to this? Well, it's equal to this at pi over 6 and 7 pi over 6, when theta is equal to those. Now, which of those do we need? Well, let's diagram our point. So -2 root 3, and then -2 here. So this is the real axis and the imaginary axis. So this is in quadrant 3. The angle that is also in quadrant 3 is 7 pi over 6. So this is the appropriate angle. This one is not. And we can write this as r, which is 4 times the cosine of theta, theta being 7 pi over 6, plus I times the sine of 7 pi over 6. And there we go. So we've done one for each quadrant, and then one that fell on each axis to do a demonstration here. Hopefully this is pretty clear and not too difficult to understand. If I need to do some more examples, I can do those in a later video.